Okay, welcome to 6-4 central limit theorem. It's actually a super basic concept, but like a big idea. So let's read the definition and then I'll explain the definition and then I'll show you a couple of problems. For all samples of the sample size n, where n's greater than 30, so you have a bigger sample than 30, the sampling distribution of means. So let me highlight this right here, right? I got a purple highlighter. That is our means. And that's really important. The sampling distribution of the means can be approximated by a normal distribution with the mean and standard deviations like this, but the standard deviation has to be a little bit different. So that's important as well. So all it's saying is if you have a sample size of 30, and I don't care how your original data is the sampling distribution, it could be uniform, it could be skewed to the left, skewed to the right. I don't know if I showed that the right way. The tail goes to the right, it's right skewed. If the tail goes to the left, it's left skewed. It doesn't matter. It could be a distribution we haven't even talked about, right? Data doesn't have to be normal, right? It doesn't have to be a bell shape. It is in a lot of cases, but it doesn't have to be. It could be a bunch of different shapes, and it doesn't make it the data bad or anything like that. It just is a different shape. No matter what shape that data is, if we have more than 30 and we take the means, not the data values, the means, then we can use normal to find the probability or anything else that we want to find that we can use the normal for. So that's the idea of the central limit theorem, is I go from some kind of sample and then I look at those means. That's why I point out the means. So let me show you this wording stuff. Read through it if you'd like. It's really, what is it talking about, and trying to explain this, what I just am saying to you right now. So if I look at this first problem, it says, assume that the females have a pulse rate that are normally distributed with a mean of this, and so forth. It says, if one adult female is randomly selected, find the probability that her pulse rate is less than 83. So assume that females have a pulse rate that is normally distributed with a mean of this and a standard deviation of this one. This one said they're normally distributed, okay? And it gave us these two informations, but it said we are looking at means, which is what we're looking at here because this is the symbol for a mean, right? You have a mean of a sample and a mean of the full population. That's still the mean. So that's the mean of the population. So what we're going to do is we're going to take this mean and we're going to take the standard deviation that was given. And we always have to take the standard deviation and divide it by however many people we're talking about, how many means. We only have one mean on this part A, okay? So this really just ends up staying the same number, but I want to point out that it is the square root of 1. That is the rule, okay? And then we would put this in to StatCrunch to find the probability, and it would look like the probability of X is less than 83, less than 83. I think StatCrunch automatically does less than or equal to, and then we have to find that probability through that normal calculator. And we can use the normal calculator because why can we use the normal calculator? Because that's the whole rule of this idea, is the means are normally distributed. So let me pull up StatCrunch. I was already in it. Let me close that out. Remember, you go to Stat Calculator. It's the first one here. It usually looks like this, Calculator. We have to find the normal, and it should bring this up. And remember, we have the between section and the standard section. This one, we need the standard section because it says less than 83. So we have to have less than 83 here. And then our mean that we're going to use was 77. And our standard deviation that we'll use is a 12. And it'll give me my probability, which is 0.06915. They usually would like you to round 4 decimal places, so we'll go out 4 as well. Now for part B, it says now we have 9 adult females who are randomly selected. Find the probability they have a pulse rate of a mean less than 83. So same less than 83, but now we have 9 people that we're going to have. So what we'll do is we still have that same mean, but now our standard deviation will be 12 divided by the square root of 9, because now we have 9 people instead of just 1. Okay, so square root of 9 is sometimes 3, right? 12 divided by 3 is 4. So a lot of the problems you have to use your calculator for that because they're not pretty like that one. Okay, so I need to just change the standard deviation over here to 4, and everything else stayed the same. We want the 77, we want less than 83, which we can see is all the same on this one. So let me write that probability of x is less than or equal to 83 is now going to be a very different probability. 332, rounded up at the end. So that is our probability on that one. So they're very different, one person versus 9. So that's the main idea of this one. We're looking at means because that's what this is all about. So part 2 here, or problem 2, excuse me, has an elevator. Let me just go to the problem so we can see that a little bit better. Otherwise, it's super small. So an elevator has a placard. I think it I don't doesn't feel like that should be the way it's spelled, but I got this out of the book, so it probably is spelled that way. A placard, so stating that the maximum capacity is 2,560 pounds. Getting on an elevator, they all tell you how many pounds are allowed on that elevator. 16 passengers can fit on this. So it says, oh, 16 people's good or this weight, right? What if everyone that gets on is a male, right? So 16 adult male passengers can have a mean weight of about 160 according to that placard card. That's pretty low. If the elevator is loaded with 16 adult males, find the probability that it is overloaded because they have a mean weight greater than 160. Well, we all weigh a lot in my house, so I'm thinking that definitely should be overloaded on that. But assume the weight of males is normally distributed with a mean of 165. So they're giving us the standard deviation and this mean of the sample. So we'll use that mean of 165, and we'll use that standard deviation of 31. Now, when we divide that standard deviation by that square root piece, how many people are we trying to load on, or how many people are in this group? 16. So we're going to have to do 16 here. So the square root of 16 is 4, but I don't know what 31 divided by 4 is. So I get 7.75. So then that is our information we can put in. So we'll have the probability as this is, we want to be greater, no, yep, greater than or equal to the 160 on the card. So we're using our sample data to see if that placard, what's the probability of, that not being very good. I keep wanting to use my mouse and show StatCrunch on my computer, not on my iPad. Okay, so we're going to change this here to 165, which was our mean that we were given. And now we want 7.75. So I've changed that standard deviation to be what we need. And we want 160, but we want greater than 60. Okay, so there's our answer. We're greater than 160, and our probability is 74%, 0.06. Okay, there we go. 0.7406 or 74.06%. How safe is the elevator according to our information that we got, which is the placard, what the placard said with the 160 and our sample with the 165? Does that appear safe? Absolutely not. No. 74% chance of the elevator plummeting down and crushing. No, no thanks. I'd like that to be like 1 or 0. So way too high of a probability for an elevator. Okay, so you can see the idea of the square root. The last question here, I'll just leave it small, but this is the overhead reach of an adult female. So we're overhead reach of adult female. They are normally distributed with a mean of 204 and a standard deviation of 8.5. Find the probability that the individual distance is greater than 216. Okay, hang on real fast. Okay, so for this one, we have our 204 for our mean. So we got to put in our 204 over here. Oops. And the first one is still just find the probability of an individual. So just one human. So we'll keep that same standard deviation because 8.5 divided by 1 is still 8.5, right? The square root of 1. But this one is asking that it's greater than 216. So we're trying to see how many people have a greater reach than 216. And that is a super small probability here. So the probability of x being greater than or equal to the 216 is super small, which is 0.00790. Okay, so 7%-ish. So it's not, women don't have that big of a reach. Okay, a greater reach than that. Okay, for B, same idea, but now we have 23 randomly selected. So now we have to take that standard deviation, right? And take 8.5 and divide it by the square root of 23. And when you get a decimal, because this one's definitely a decimal, you need to go out quite a few places. Let me find this answer real quick. Oops, root of 8.5. I didn't type it in right. Oh, I typed. That's funny. Okay. I got 1.7723, whatever, 4 something. It keeps going. I rounded off to a 4, so I didn't write it down with the wrong round. But over here, I'm going to go out quite a few places because if I want the final answer to be 4 decimals out, you better not round anything, less than 5 or 6 decimals out because then it will round wrong for your answer. So 7.723.725. So I went out a bunch of places, and we still have greater than, right? Oh, it also didn't have the 216 here. Same thing. For some reason it didn't print. Okay, and then compute, and look at how it gave that answer, right? That answer over here. It almost let me circle it. Usually it doesn't let me do that. Compute is so small that it's in scientific notation, and it's like this number, move the decimal 12 places to the left. That's what negative is, right? So it's at 6 point right now. So we're going to move the decimal 11 places. So one move, or 12 places, excuse me. One move will make us to be at 11, and then you add 11 zeros. So it's 0.11 zeros, 6413, the number there. That's pretty much 0. So the answer for the probability of this one is pretty much, it's like 0.00000. I don't even want to write out all those zeros. Okay, here's another little bit of an idea here. It's like, why can the normal distribution be used on this one when I didn't have 30? I had 23 because the population was stated to be normal. Now, if the population wasn't normal, we can still use this, but we need 30 or more. All right, that's it for this section. Lots of normal calculator stuff in your StatCrunch.